Yeah. So good morning and good afternoon, everybody. Today, first of all, we are continuing the series of IGAC ECR skill workshop, and we would like to welcome everyone to this workshop. Before we begin today's presentation and workshop, I would like to introduce our speaker to the audience. Dr. Piyushkumar Patel is an interdisciplinary atmospheric scientist and remote sensing expert with over a decade of experience studying aerosol, cloud, and climate interactions, pollution emissions using satellite remote sensing to understand global climate change impact. Now, recapping his journey, Dr. Patel has worked in Indian Space Research Organization, Indian Space Research Organization, where he contributed to satellite calibration and geophysical product validation across multiple laboratories. He subsequently served as a NASA postdoctoral fellow at a Jet Propulsion Laboratory in California, pioneering the novel retrieval algorithm to estimate CCN, cloud condensation nuclei, from spaceborne LiDARs. He then worked at MethaneSat in Texas before joining his current position at SRON, the Netherlands Institute of Space Research. Dr. Patel develops advanced aerosol retrieval algorithms and AI-driven quality filters for multi-angle polarimetric satellite data, enhancing the understanding of cloud, aerosol, and their interaction and climate implication. His work bridges satellite observation with atmospheric science to drive discovery and climate solutions. So we are privileged to welcome Dr. Patel as a speaker in today's talk, From Data to Discovery, Advanced Satellite Remote Sensing for Atmospheric Science. Welcome, Dr. Patel.
Thank you, Pravas, for a nice introduction. Hi, everyone. So as Pravas mentioned, today I'm just giving an overview about the advanced satellite remote sensing, or I'll say start from the first satellite for the atmospheric science or aerosol. From there to till date, like what are the technology we have and how we are measuring particularly the atmospheric aerosols, and small portion for the clouds. So I hope everyone knows about the atmospheric aerosols. So it's just a particle suspending into the atmosphere, which size varies from nanometer to a micron. And there are the various type of atmospheric aerosols, and it has a different impact on the climate and on the air quality and the health. Although my research is focused on the climate side, so I'll talk mostly about the climate. So how the aerosol affect the climate? So there are major two effects. One is direct, or we call aerosol radiation interaction, and the second is indirect, which call aerosol cloud interaction. So first, if you see the figure in the red box, which shows that when you have the aerosol into the atmosphere, which scatters or absorb the radiations, solar radiations particularly, and that is called direct effect. So that varies the total radiation budget by absorbing and scattering the radiations. Now there is a second effect we call indirect effect, where the anthropogenic aerosol particularly, which act as a cloud condensation nuclei or the ice nuclei and forms the cloud or the cloud droplets. And these cloud droplets are smaller in size. And because they are small in size, you have a large surface, and that large surface reflects more radiations to the space. Again, and that is called the first indirect effect or TAMI effect. Now these smaller cloud droplets will take more time to turn into the precipitations or rain droplets, and that actually delays your rainfall or precipitations. So that is called second indirect effect, or also the cloud lifetime effect. And there are one more effect we call semi-direct effect. So in that, we have a smaller size of clouds, and they are surrounded by the absorbing aerosol, mostly the black carbon or the dust. And those absorbing aerosols that absorb the radiations and warm the surrounding of the clouds. And because of that warming of the surrounding, the cloud get dissipated, and that is called the semi-direct effect. Now, if you know the IPCC reports that every 6 years they publish numbers for different atmospheric compositions, how they affect the radiation budget. So this is we call the first IPCC report, which is published by Hansen. And if you'll see the numbers within the red box, so they are the very general numbers like tropospheric aerosols, how they contribute to the total radiation budget, and the tropospheric aerosol for the suit. So we have some numbers. After 6 years, the second assessment report came in 1995, where we have some more development in the aerosol science, and we come out with the more precise numbers for the aerosol forcing, and those total aerosol forcing are still 1.87 watt per meter square. Later on, we have a more development into the climate modeling, particularly, and then we are come up with the another number, which is 2.36, which is quite higher than the, the first one. And then come the IPCC report in 2007, where we actually identify the direct effect and the cloud albedo effect, which is the first indirect effect. And we have given two numbers, one for the direct and we have one for the indirect. And the total number is still a 1.7, which is reduced from the previous report. Then come 2014, again, some more understanding of aerosol and cloud, and we come up with the some smaller number than the previous one. And very latest reports in 2021, which came and shows that still we have a more understanding of the aerosols, how they affect the climate, and we come up with the still smaller number than the previous one. Now, if you'll see the pattern of these numbers, so after 2001, the numbers are getting reduced. So what exactly happened after the 2001? So if you remember in the 1999 and 2002 or 2001, sorry, we have a launch of multiple Earth observing satellites, which are MODIS, MISR, OMI, sorry, not the Kellogg. So these MODIS and MISRs are launched in 1999 in Terra and in Aqua. So those satellite has given, so if you see in this figure, these are the global distributions of aerosol optical depth. And this satellite has given a real picture of the aerosols, and those observations has implemented into the climate model. And that actually leads the reduction of the uncertainty. Now, if you see, we still need some more informations of aerosols, which can reduce this number furthermore. So if you'll see this very nice two different images of MODIS, one from the California coast, which shows the smoke coming from the Bahamas burning, wildfire. And the second on the right side, you can see the dust emitting from the African region. Now, the important thing is that what are the parameters? Like, it is easy to see that, and we can, by visualization, we can say that, okay, there are the aerosols, and you can easily identify the difference between the clouds and the aerosols. But what are the variables we still need to understand this aerosol effect on the climate or on the air quality or on the health? So that is the question. Now here, if you'll see over the ocean, it is easily identify the aerosol, but if you'll see over the land, it is particularly in the dust picture, it is still difficult to identify the contribution of land and the contribution of aerosols when the aerosols over the land. Now, these are the wish list that we need to reduce the uncertainty into the climate model. The first is how much and where the global distribution of AOD. Second is how much is backscattered to space. So how much is radiation backscattered to the space? That depends on the properties of the aerosol. The third one is how much is absorbed in the atmosphere. Fourth is how much above the cloud. So that is also, I will discuss more about that, but that is also the necessary thing. And the fifth is what are the cloud properties with and without aerosol presence. So that is the particularly a task for the climate model, but we still have to understand that how the aerosol affect the cloud properties. Now, as I mentioned that there was a first satellite we call MODIS, and a similar one more sensor we call VIRUS or VIRS. That is a identical brother of MODIS, but a more developed way. So MODIS has launched in Terra and Aqua. Terra and Aqua are the satellite. MODIS is the sensor. Terra is launched in 1999, as I mentioned. Aqua is launched in 2002. And these are the variables what this particular MODIS has provided, which is aerosol optical depth, angstrom exponent, and aerosol types. And the both Terra and Aqua has the similar spatial resolution 10 kilometer. After for a few years, the other one more product came with the new algorithm that provides the AOD product at 3 kilometer. Now, this, if I talk about the identical brother, which is VIRS. So if you'll see, they are, so till now, the three VIRS instrument has launched. One is in Xiaomi NPP satellite, launched in 2011. Another two is in NOAA 20 and NOAA 21, which are in 2017 and 22. Further two missions are planned where this VIRS instrument has been installed in these two instruments. And the VIRS also is providing the same similar aerosol parameter from the space, but it has a high spatial resolution, which is 6 kilometer. Now, if I'll talk about what are the algorithms used for the retrieval of aerosol from the MODIS. So there are major two algorithms are there. One is dark target algorithm. So dark target algorithm, I'm not going to explain everything, but very general way, the dark target algorithm works very well on the ocean and over few land surface type. But if you'll see these gray portions where this AOD, so there is particularly no data where we don't have AOD data from the dark target algorithm. Now, what are those surfaces? So if you'll see in the pole region, they are mostly the ice. And this region, which are a desert region, so Northern Africa, Middle East, part of India, and part of China, which is Gobi Desert, and gray area in the Australia, the middle region of the Australia, which is again the desert. So basically, the dark target algorithm won't work on the bright surfaces, I'll say, because ice and the desert both are the bright surfaces. So over the bright surfaces, basically the dark target algorithm where the wavelength has choose to retrieve the AOD, those are getting confused, and that's why we don't have the very accurate or precise informations of AOD over the bright surface. And therefore, the new algorithm came, which called deep blue algorithm. So in deep blue algorithm, they just switch the one wavelength, which is 490 nanometer, which used in the dark target. They switch from 490 to 412. Now, if you'll see the right side picture, so 412 you can see some of the aerosol features over the land surface, which you can only see in the 412, but not in the 490, which is just down to the RGB picture. So this deep blue works very well on the bright surfaces, particularly a desert and the ice. Still, a polar is not there because these are the polar orbit satellite, the MODIS and all. It won't cover the entire polar region. But if you'll see there are certain observation we have over the Himalayan regions. But if you'll see that the desert picture, so now desert is completely blocked in the dark target. But if you'll see in the deep blue, we have a very nice informations of aerosols over the desert surface. So these are just for the comparison. Now there are few more satellites we have. One is MISR. So MISR is a very innovative approach they have given that is also launched in the Terra. And MISR actually measures the Earth in a different angle. So we call multi-angle imaging spectroradiometer. So you have information from different angles. So your instrument at single rate, but you have information from the multiple angle. And that multiple angle information will give you the informations from the different perspective of any object. So here the object is the aerosol. So you will get the aerosol information from different angle. And because of that additional features of multi-angle observations, you will have the information of particle size and shape, which is not available into the Moody's. Moody's will only provide the aerosol optical depth. There is an angstrom exponent, which you can use as a proxy for the size, but it is not exactly the size. But in the miser, you will have the particle size and shape information along with the aerosol height information, which is very much required when you calculate the radiative forcing, but in a specific cases. Then there are another two instruments called OMI, Ozone Monitor Instrument, and the TROPOMI. So OMI has launched in 2004 in ORA satellite. The TROPOMI has launched recently 2017 in Sentinel-5P. So now the advantage of OMI and TROPOMI that they have a one UV channel, which is around the 300 to 400 nanometer, and that UV channel will give you the UV aerosol optical depth, which is highly sensitive for the anthropogenic aerosol or the smaller or fine mode particles. And we have the additional variable called absorbing aerosol index, and that will actually give you the information about the absorbing aerosols, particularly a black carbon or the dust. And we also have the single scattering albedo, which is very much important when you calculate the radiative forcing. But they are still a coarser. The OMI is particularly a coarser inside. The spatial resolution is very coarse compared to TROPOMI. But now all this, the past instrument, I will still say, but still Morris is working, but still a past instrument. Those instrument has given the information in our wish list, how much and where the aerosols are in terms of global distribution. They provide some information of the backscattered to the space, like single scattering albedo, or you can say the aerosol index. But we still need more informations about the how much is absorbed in the atmosphere. We have the SSA information from OMI and TROPOMI, but still they are not that accurate that we need for the calculation of radiative forcing from the climate model. And we also need the information of how much above the cloud aerosols. Now, very latest report came before this new satellite, a bunch of new satellite has launched from the NASA that they say the aerosols, now we get this understanding that aerosols are smaller particles because of these all satellite observations in the air, and that can either cool or warm the climate, depend on their characteristics, and depending on the type and color the particles. Now, still, we have a question that what are the type, aerosol type, and what are the color of the particle, color in terms of the size, shape, and what is the chemical properties of the particles. Now, we still have to answer these, the red portions of the sentence. And therefore, we have some advancement in the satellite remote sensing. Now, before I'll jump into a new satellite, there is one more additional satellite launch by the French. It's called Perazol. No, the satellite name is Polder. In that, the instrument name is Perazol. So the beauty of the Perazol is that all Moody's, Miser, OMI, TROPOMI has just measured the radiance which are reflected from the Earth's surface, but the Perazol has the another thing which we call polarization. So it measures radiance along with the polarization. So the polarization will give you the more accurate information about the aerosol size and shape. So the Perazol has been activated for like 4-5 years. It was just in demonstration, but within the 4-5 years, it has given a lot more information than the Moody's and Miser, particularly about the size and the shape of aerosols. And then after we have a 10 years of gap and we don't have any polarimetry into the space. And then very recently, last year, we have another satellite called PACE. So PACE has a total 3 instruments. In that, 2 are the polarimetry. One is SPEX1, which is from my my company, and the another is HARP2, and there are few more is lineup that I will discuss later. Now I'll talk about the PACE, which is very interesting instrument. So PACE has a major three instruments, or total three instruments. One is Ocean Color Imager, OCI, which is again a same like MODIS, a spectroradiometer, which is developed by the NASA. And the second instrument is HARP2, or Hyperangular Rainbow Polarimeter, that is particularly developed for the cloud measurement, but we can also measure the aerosols for that. But it has a limited number of wavelength bands. OCI is a hyperspectral, the first one. The HARP2 is a multispectral. And then the third comes SPEX1. So the OCI only measures the radiance from one angle, or we can call the field of view. HARP2 measures the radiance and the polarizations from different angle. So it has a 3 bands with 10 different angles, and there is a 1 band, it has a 60 different angles. So these 60 different angles will use for the cloud retrieval. And then after comes SPEX1. So SPEX1 is again the hyperspectral. So you have a information at each 2 nanometer interval from 380 to 770. And the spatial resolution is 5 kilometer, and it has a 5 different viewing angles. So you have a lot more information. You have a radiance, you have a polarization, you have these two information, the radiance and polarization for each 2 nanometer spectral band, and at 5 viewing angle. So these 5 viewing angle for each wavelength. So you have a lot more information than the MODIS or MISR or any other previous satellite datasets. Now, if you see, this is the PACE instrument on the top, and yeah. So if you can see this is the OCI, and here these two small boxes, HARP2 and the SPEX1. So if you see, OCI measures the only one angle, which is the field of view from -20 to +20. Then after comes HARP2. So HARP2 has a multiple angles, and that you can see that how it measures. And then after comes SPEX1. Yeah, so this SPEX1 has the 5 different angles. So it measures the radiance and polarization for each 5 different angle. And if you see on the right side, that shows the spectral coverage of each instrument. So OCI has from gray to, so don't get confused between the red, gray, and blue. I just want to talk about the spectral coverage. So it starts from like around 340 to 2000 nanometer. HARP2 has only 4 bands, and SPEX1 again a very continuous hyperspectral instrument. Now, if I'll talk more about the OCI, so OCI is ocean color instrument. So because it has a hyperspectral instrument, we can use OCI, but OCI is made for the ocean color measurements and ocean, particularly for the ocean measurements, but we can still use for the aerosol detection because of their hyperspectral characteristic. So for ocean color instruments, which is already, so there are multiple algorithms which are developed by the NASA GSFC, and they use same algorithm what we use in the MODIS, like deep blue, dark target, and near UV, that is for single scattering albedo retrieval, which are already used in OMI and TROPOMI, but this is just a upgraded version of the same algorithm. So these 3 algorithms used for the aerosol retrieval from the OCI. And if you'll see what are the variables we have, so we have aerosol optical depth, we have a above cloud aerosol optical depth, which are very much required because this above cloud aerosol optical depth affect the cloud property, as well as it also affect the radiations which going back to the space. So when you don't have the aerosol above the cloud, this radiance, also the radiation which going back to the space are different than when you have a aerosol above the cloud. So that's why we need this aerosol above the cloud information. So we have a aerosol optical depth, above cloud aerosols. We have a single scattering albedo from the 2 different algorithms. One is NUV and the dark target. And the additional variables, we have this aerosol layer height, aerosol index, and the fine mode fraction, which shows that how much is the fine mode dominated for a particular space and time. Now, if I'll talk about Specs 1, so Specs 1 is made by my company, Asron. As I mentioned, it has 5 different angles. So it measures the radiance and polarizations at 5 different angles. This right side plot shows the hyperspectral variations for each angle. So V1, V2, V5, V4, V3 are the 5 angle, and the bottom 5 and the top 5 are the polarization. So now we have the 2 informations instead of 1, like we have a radiance at each 2 nanometer interval and a degree of polarizations that also at each 2 nanometer interval, but for 5 different angle. So these are the informations. You can see the radiance and DOLP. These are the information we have from the Specs 1. But if I'll talk about the Moody's or Miser or anything, particularly the Moody's, which has only one single line out of these 5, only the radiance. Now you can see that how much information we have from the new technology. Now, if I'll talk about the parameters, what we are getting from the Specs 1. So we have a very traditional variable aerosol optical depth, angstrom exponent, and single scattering albedo. So this is the 1 year of combined data sets. And the bottom, you can see how they are very seasonally. These are the first year of data sets. Now, because we have a more information from the instrument, we can identify the different species. So you can see we have a dust, we have a fine mode non-absorbing, we have a black carbon plus brown carbon. We also have a sea salt and the aerosol water. So what is aerosol water? Aerosol water is that how much water aerosol can bring along with. So we also call aerosol uptake. Yeah, the water uptake. So now we have along with the aerosol optical properties, which are aerosol optical depth, angstrom exponent, aerosol index, we have additional variables like size, shape, and the chemical information. So from size and shape and chemical information, along with that, we also have the refractive indices, which we are retrieving from the Specs 1. And based on all these, we can identify the species like the dust, fine mode absorbing, black carbon, brown carbon, sea salt, and all. So if you see, these are the first left plot is fine mode effective radius. It's not fine mode fraction, it's the effective radius, which shows the size of the fine mode particles. The right side shows the particles which are under the 10 micron, which are mostly we use for the estimation of cloud condensation nuclei. And the third plot, left side bottom plot, which shows the real refractive indices. So we have 2 refractive indices, one the imaginary part and one the real refractive indices. This real and imaginary will be helpful to identify what kind of chemical species we have in the aerosol particles. And this is the aerosol index on the last plot. Now, as I mentioned, we are also retrieving the aerosol water uptake. So from the aerosol water uptake, we can see that how the aerosol having a growth with respect to the moisture available into the atmosphere. Now, how they grow. Now, based on this growth of the particle, we can estimate the chemical composition of the particle. And from that, we can also calculate the cloud condensation nuclei, that how much the aerosols turns into the cloud droplets. So now these all the additional variables will give more information about this, how aerosol affect the climate. And maybe that will be helpful to reduce the uncertainty of aerosol radiative forcing. Now, I just want to quickly take time to give an overview about the algorithm what we use to retrieve this different aerosol variable from the Specs 1 particularly. So the algorithm we call RAMO-TAP, which is remote sensing algorithm for aerosols and trace gases. This is our in-house algorithm, what we develop here in my company. So that algorithm having a kind of a lookup table. Now that lookup table, based on that lookup table, we have a first guess based on the major radiance and degree of polarizations. Now, once we have a first guess, now this first guess includes the aerosol optical properties, size, refractive indices, chemical compositions, everything which are already available in the lookup table. Now, based on this first guess value, we compared those, we calculate the degree of polarizations and radiance, and we compared those calculated values with the measured one, and we'll try to reduce the difference between them, by running the radiative transfer model and the aerosol inversion algorithm. And once we have the closest calculated and the measured value, we'll consider those aerosol variables as an aerosol retrieval from the polarimetric measurements. So as I mentioned, our algorithm has three size distributions. One is fine, the second is coarse soluble, and the third is coarse insoluble. So coarse soluble are mostly a sea salt, and the coarse insoluble are dust. So we consider these three different modes in our algorithm. And as I mentioned, we are also retrieving the refractive indices. And this refractive indices with respect to wavelength will provide the information of what kind of chemical composition you have. So you can see this, how the variation of refractive indices for different species like brown carbon, dust, or the black carbon. Now, these are the variable list what we are providing from the specs one, which are effective radius, the variance, real refractive indices, the species, number concentration. It's a spherical index. So what kind of particle we have? It is sphere or non-sphere. Mostly the dust are the non-sphere. And we have aerosol layer height. And that for fine mode, for coarse insoluble mode, and coarse soluble mode. So these all variables are available in three different modes. And also we are retrieving some surface informations. As I mentioned, we also need the surface information, which we have to remove from the total radiance value or total polarization value to get the aerosol contribution in the radiance. And we also have along with the size and chemical, we also have the optical properties. Now, these algorithms are based on the physics. Now we are trying to switch the algorithm based on the neural network. So this is still an under development, but yeah, I thought it's good to demonstrate. So we are now training the neural network based on the radiance and the degree of polarization what we got from the measurements. And we have the lookup table where we have all the aerosol informations. Now, based on that, we are training the neural network algorithm, and then we are retrieving a few variables like aerosol optical depth, angstrom exponent, single scattering, and cloud fraction. So cloud fraction, which is used also for the cloud masking, or I can say remove the cloudy pixels, because aerosol can only retrieve during the clear sky. For the cloudy pixels or cloudy sky, we cannot retrieve the aerosol because the cloudy pixel will give you a lot of uncertainty in the aerosol retrieval. So we need cloud information to remove those pixels which are covered with the cloud. And these cloud fractions, which are retrieved from the neural network, will helps us to remove those cloudy pixels. Now, this particular neural network based development, we compared with a ground based measurement of the AeroNet, and we found very good correlations, but still we need some more tuning of the neural network. So that is still under development. Yes, we are also developing the machine learning or neural network based data quality filtering. So now the data quality filtering, when you use any satellite observations, that is very much required that you choose only those information that has a very precise aerosol informations. And for that, we need to use the data quality filtering. Now, this data quality filtering depends on a few factors. One is how is your atmosphere for the given pixels? Like, is it cloudy, or maybe you have a sun glint? So that the one and biggest factor is that how your atmosphere for the given pixel. Now, whatever the measurements you have, like radiance and the polarization, how accurate it is. So when you have a multiple angle informations, you have a very precise information from a straight look, which we call nadir look. But if you'll go far from your nadir or normal, you are adding some more uncertainty in your measurements. So that will actually affect your retrieval algorithm. So second factor is that how your measurements affect your retrieval algorithm. So retrieval algorithm have some confidence or have not some confidence. Based on that, also we derive the data quality filtering. Now, this new machine learning based algorithm, that is not only the machine learning, but we are also using the physics for that. So we are using the surface variables. As I mentioned, the surface informations are very much important when you retrieve the aerosol. So we have some surface variables, almost 9 or 10 variables. Uh, Along with that, we have the aerosol informations, and that goes into the clustering model. Based on the clustering, we are dividing the surface. And for what kind of surface, we have the accurate measurement of aerosols. That informations we are extracting from the clustering models. And then we are training the machine learning model. So the model can identify what type of surface you have, what type of aerosol signal you have. And based on that, we are identifying, or the model can identify or give you the number of uncertainty, or the we call GCOS value. So GCOS is the value required when you use any aerosol variable from the space. So that value is the uncertainty value defined by the global community. Now we have to be in that thresholds, which we call GCOS. So this GCOS, or the uncertainty value, this machine learning model will give you based on the given surface and aerosol values. So this is a kind of a new physics-based machine learning model, or the neural network model we are using to develop the advanced quality filtering. And this is the comparison with AeroNet. We have recently published this paper. This is from the physics-based model, but not with the neural network model. So we found that we have a very robust correlation between the SPEX1 and the AeroNet. AeroNet is a ground-based network for the aerosol measurement developed by the NASA. We have also very good correlation with the angstrom exponent. We found some correlation with the single scattering albedo, but we still have a relatively large bias, and that because the single scattering albedo methodology retrieved by the SPEX1 and retrieved by the AeroNet are different, and because one is measuring to the ground, at the ground, and one is measuring at the space. So we have a different atmospheric path, and these atmospheric path variations have the different impact on the SSA retrieval. And that's why we have some kind of bias. But other than that, we have a good robust correlation between the AOD and the angstrom exponent. So this is just a one AOD we have demonstrated for just sake of the presentation, which is 550 nanometer, but we are retrieving AOD at 18 different wavelengths. As I mentioned, that is a beauty of the SPEX1 because it is a hyperspectral satellite or sensor. After SPEX1, we have a HARP2, another polarimetry, but multispectral for cloud. And from there also, we are trying to retrieve the aerosol information. And that is actually handled by the UMBC, because this instrument has developed by the UMBC, USA. So they already have algorithm we call the algorithm called GRASP. So GRASP is an algorithm developed by the scientist called Oleg Dubovik from France. He was in NASA, but now he's France. So he developed his own algorithm for polarimetry, and which are more or less similar, like our algorithm, what I mentioned, the RemoTap. But in HARP2, the GRASP algorithm has applied. And if you can see, they are also retrieving the aerosol optical depth, fine mode aerosol optical depth, angstrom exponent, single scattering albedo, and the coarse mode AOD. So this is for the picture of forest fire smoke. If you see the pollution over the Indian Peninsula, you can see very bright patch here, the high AOD value. And you can see they are also retrieving the angstrom exponent, SSA, and the coarse mode AOD. So there is almost no coarse mode AOD, but you will see mostly the pollutions. That's why we have a high AOD fine mode. Yes, that is also same for the dust. So for dust, it's other way around. Like we have a very less fine mode AOD, but we have a very high AOD coarse. And this is the AOD overall retrieval from the HARP2. Now, There are one more algorithm which are developed by the UMBC. They call fast maple. So fast maple algorithm only works on the ocean surface, not on the land surface. And they are also trying to retrieve the aerosol informations more accurately. So we have aerosol optical depth, single scattering albedo, fine mode volume fraction from this ocean surface. So you can see easily, you can identify the smoke, like we have over the California early this year. So these are the smoke plume, which you can see in the fine mode fraction very easily. Also in the single scattering albedo. So the blue shows the highly absorbing particles. The reds are non-absorbing kind of particles. So this new algorithm also provides the very good, more detailed informations about the aerosol over the ocean surface only. Now, basically, the HARP2, as I mentioned, made for the cloud measurements. So these are the cloud variables, what they are planning to, or they are already in a halfway to retrieve those variables like cloud top heights, optical thickness, top phase, what kind of clouds you have, ice or water, drop effective radius. So what are the radius of droplets and the variance? Based on the radius and the variance, you can actually get the full size distribution of the cloud droplets, and then ice effective radius and ice crystal shape and scattering properties. Yeah, I'll just keep this. So yes, this is a picture of cloud effective radius, but not from the HARP2, but that is from the OCI, ocean color imager. It has an algorithm called bispectral algorithm, and based on that, they are retrieving this cloud effective radius. Now, the other limitation of this bispectral retrieval algorithm. Before that, I'll talk about the advantages. So advantages that will give the information at very high resolution, which are 1 kilometer. Same as MODIS, like same algorithm applies in the MODIS, but in OCI it is more upgraded version. You also have the information at a large, so OCI has a large field of view, so you will get a large area covered within a single orbit. And we have a high quality for most stratus cloud informations. But what are the cons? The cons is that the bispectral algorithm won't work when you have a smaller clouds, or you have a broken clouds, you have a mixed phase clouds. So mixed phase clouds when you have ice and liquid both together, or you have a precipitating clouds. So in this scenario, your bispectral algorithm won't provide the accurate information, and it has a large bias in the failure rate. I'll skip this one. So how the HARP2 will help to identify the, or to provide the more accurate information. So if you'll see in the left sides, we have a normal cloud imager or cloud camera picture. You can see that how clouds is passing by. And on the right side, if you'll see, there's the same again camera, but it's a polarized reflectance. So we have a polarized filter we put on the cloud, and you can see kind of a rainbow kind of a structure. And that is actually polarized signal of the clouds. And this rainbow kind of structure we call cloud bow, because it does not has the 7 colors. But yes, this cloud bow, which is the polarized signal from the clouds, will help you to give informations or more accurate informations of the cloud properties. Now, once we have these cloud bow informations, it is very simple algorithm to retrieve the cloud informations. So you just put these polarized signals of the cloud bow into the mu calculations and just run the mu for the different size, and you will have the phase functions or the spectra at different scattering angle for different cloud effective radius. And based on that, you can identify what kind of effective cloud particles or cloud droplet number droplets are available. Now, how we are retrieving these informations. So these are the polarized reflectance what we got from the cloud bow. Now at around 130 to 150, sometimes you will get this kind of peak when you have the liquid clouds or liquid top clouds. And based on that peak, you can identify what kind of cloud you have, what kind of cloud phase you have. One is liquid, and if you have a flat, you can say it is ice top cloud. Now, based on the magnitude of this peak, you can identify. So we calculate the index called liquid index, And based on the liquid index, also we can identify which is ice cloud or the liquid cloud. And this magnitude also help you to retrieve the um, cloud droplet size distribution. Now here is the picture of overall liquid index from the HARP2. So the pink or red color shows the liquid clouds, and the blue color shows the no cloud or the ice clouds. So it is very easily you can identify what kind of cloud phase available. I'm not going into the detail, but yes, this is the algorithm what we use for the retrieving the droplet size distribution, which includes the effective radius and the variance. Now, if you'll see here in this plot, we have a different refractive index and how the variance affect the plot. So the variance here is like 0.018 for different effective radius. Now, if you'll see the next plot, the effective radius are same, but just changing the variation, how the spectra has changed. So based on this variations or difference in the spectra, you can also calculate the variance of the cloud droplets. Now, these are the pictures. The left side shows the liquid drop effective radius, and the right side shows the effective variance. Now, based on both radius and variance, you can calculate the full size distribution, like we have the aerosol size distribution. Similarly, we have the cloud droplet size distributions. Now, the question is, we have a one radiometer, we have a two polarimetry into a base. Now, we have a more detailed information than the previous satellites like MODIS, MISERS and all, and very advanced satellites. Very detailed information they are providing. But is this enough to reduce the uncertainty into the climate problem? Question is still there. And the answer is maybe. So when I started working on these presentations, I was convinced that PACE would only open the more questions and also increase the uncertainty, because that is what we remember from the MODIS data. So MODIS has given a lot of informations, and that actually reduced the uncertainty, but we still have a more question, like we need size information. We come out with okay, we need size information, we need safe information, we need chemical informations. Only the global distribution won't work. Similarly, when PACE will provide the size, shape, and the chemical information, it may possible we have still more questions come out, which can further advance the technology and may be helpful to reduce the radiative forcing uncertainty into the climate model. And finally, so the answer is maybe that can reduce the uncertainty, but that depends on how well the instruments perform over the long term. Like if you see difference between the MODIS and MISER. So MODIS has worked very smoothly for like more than a couple of decades, but MISER has a lot of issues. Same as Parazole. Parazole only works for 3-4 years, and because that 3-4 years of information are not enough when you have to understand the aerosol impact on the climate. So the first question is how well the instrument perform over the long term. The second is how accurate the algorithms are. So we have a multiple algorithms for multiple surface, which we haven't seen in the MODIS. Later on, MODIS has the two algorithm, but now we have more algorithms which can provide which can provide the more accurate information for specific cases. And based on that, we can provide that more accurate information, case basis, more accurate information to the climate model to improve our understanding of aerosol and cloud. Now, the third question is how creatively users manipulate the data. That is also very much important, that how accurately the users can use these multiple informations from the data to provide more and more understanding of atmospheric processes or the processes of aerosol with the climate or maybe with the air quality. And the last one is how aerosol and cloud products are used together. That also will give you the informations, the variations in the informations about the aerosol cloud interactions. Now about the wish list. So we already hit the 2 points. Now the third point, how much is absorbed in the atmosphere. So we have a detailed information of chemical composition and the size and shape that will answer this question. The fourth is how much above the clouds we have. So we are also retrieving the aerosol layer height and above cloud AOD. So that will give the information about how much above the cloud we have. And the fifth one, that depends on that how we are using these aerosol and cloud products along with the climate simulations or model simulations to answer the fifth one. But we are still hitting the a more number of V's list than the previous satellites has done. Now there are one more technology I thought I had to cover. We call LiDAR. So we covered the spectroradiometer, we covered the multiple angle measurements, we covered the polarimetry. Now there are one more technology for the aerosol retrieval we call LiDAR. So we already had the Calliope or Calliope is a LiDAR which is installed in the Calypso satellite. So LiDAR is an active satellite. So it has their own source. It emits the light and it measures the same light, same reflected light back from the Earth. So Calypso is launched in the 2006 and it works more than 15 years. Recently, it shut down. It has a two wavelength, 532 and 10640 nanometer. The advantage of the LiDAR is that it will give you the more accurate or more, it has a very fine spatial resolutions. Also, it provides the information vertically. So all these spectroradiometer or polarimetry, they provide the informations for the particular atmospheric column. So you have a one signal from the entire column, but for LiDAR, you will have the information from each different layer of the within the column. So how these aerosols and clouds are very within the or the vertically or within the particular column. So that informations you can get from the LiDAR. Now, after Calypso, very recently last year launched the another LiDAR called atmospheric LiDAR, ATLID, which is installed in the EarthCare. EarthCare is satellite launched by the ESA, not ESA, KNMI. KNMI is again the another institute in the Netherlands. So EarthCare is the satellite by the ESA, but the ATLID is developed at the KNMI. And it is launched in 2024. The good thing about the EarthCare is that the Calypso only provide the backscatter radiation or backscatter radiation measured by the instrument, but the EarthCare will provide backscattering along with the extinction. So that extinction are very much important to identify the aerosol types. Although we can calculate the backscatter extinction from the backscatter, but here we are measuring the extinction along with the backscatter. And the another thing is that it only has the one wavelength, which is 355 nanometer, which are very sensitive for the measurement of aerosol particle. So the advantage is that a good wavelength for the aerosol retrieval, but only one. That is a disadvantage. And spatial resolution wise, they are more or less similar. So this is just an overview of how the LiDAR will provide the information. So you will have a backscatter coefficients, extinction coefficients, the color ratio. So color ratio will and the depolation ratio. So color ratio and depolation ratio will help you to identify the aerosol types, which are very much important parameter for the climate model or for the radiative forcing calculations. And now we have information at different altitude instead of at particular space and time. So those polarimetry and the spectroradiometers are only provide the information at 2 dimension. Now the LiDAR will give you the information at 3 dimensions. So you have X, Y, and the Z. Z is your altitude. And that provides the information about the different cloud types as well as different aerosol types. Yes, and as I think Pravas has mentioned earlier, that we also developed another algorithm for calculating the cloud condensation nuclei, which are the very important state of a particle, I'll say. So we have aerosol particle, and that aerosol particle get activated depends on the atmospheric moisture, and that activated particle we call cloud condensation nuclei, and that cloud condensation nuclei in presence of atmospheric moisture turns into the cloud droplets. So it is very much important to understand that how many or how the aerosol particle get activated. And for that, we need CCN information, so cloud condensation nuclei information. Now, getting this cloud condensation nuclei information or activation of aerosol particle depends on the size, shape, and the chemical information of the aerosol particle. Till the date, we don't have those information, so we don't have these parameter available from any satellites. But yeah, very recently we have developed an algorithm from the LiDAR. So LiDAR will give you the additional informations, and based on that, we have actually developed this algorithm we call ACLEAP, and that give you the information at of CCN at different 6 super saturation. Yeah, so you can see the vertical variation of CCN from the LiDAR. This is from the airborne LiDAR, and the right side picture shows the very last plot, DCCN at 0.4% super saturation. That shows the vertical variation of the CCN from the Calypso. So it's from the space-borne LiDAR. With that, I would say thank you, and I'm open for the questions.
Yeah, I think before we go to the hands-on session, if anybody has some questions,
yeah,
please go ahead.
Am I audible, man?
yep.
Hello. Yeah.
Yes,
Yep.
So previously, this node is having an overestimation in AOD when it is adjacent to cloud because of this cloud 3D or cloud adjacent effect, right? Because of the reflectance from the cloud, which is very bright. So is this problem tackled in the base, or it's still there, or it is minimized? I just want to know.
Yeah, it's a very interesting question. So yes, at the cloud boundary. So with the cloud boundary, you have a bright. I'll say the cloud boundaries are mostly the very bright in terms of high radiance reflected, and that actually give you the uncertainty of when you retrieve the aerosol. Now, when I talk about the polarimetry with the multi-angle, so this multi-angle things will handle that issue. So you have this cloud boundary information at different angles. So if at particular nadir location, if you don't have the, or if I'll say if you have an uncertainty in the measurement, you can check the another angle and you can get information. So basically we are working on that thing, that how we can answer or how we can measure the aerosol particle at the cloud boundary. But yes, it is answerable from the multi-angle perspective.
One small question that I had in your slide number 48. There was a peak for liquid top clouds.
Is it this one? Yeah,
Oh,
this one.
it's a 46, I guess. Yeah, this one. So, why it is that for particular scattering angle? Is this for a particular scattering angle, or I just want
Yes,
clarification?
yes. So that is the particular angle, scattering angle. You can see 135 to 150, where you have this peak. So that is the nature of the polarized nature of the liquid cloud droplets. So that will give you the peak based on the size of the cloud droplet. And this is the peak which is between the 135 to 140 or 45. And that will be useful to retrieve the information. So that is actually nature of the droplet. That's a polarized nature of the droplet, not the radiance nature. And that's
Thank
why,
you, sir.
yeah.
Yeah. And then you also suggested that by this variance, we can actually uh, recalculate the droplet spectra of cloud, right?
Yes.
So, is there any literature where you have compared this with some in situ or airborne measurements?
Actually, I want to cover that. We actually had a specific campion, the airborne campion at the California last year in September. We call PACE PAX. You can search that PACE PAX. So that was the same. We have a like what instrument we have in the PACE, the same instrument we have on the airborne, and we flew over the California, and we compared those results uh, with the SPEX one and HARP two. So I want to cover the HARP two, but just because of the time restriction, I didn't put here. But yes, we did the validation and we got the very good results also.
Thank you, sir. Thank you so much.
Anybody else? Or we move to the hands-on session?
If anybody wants to ask the questions in the chat, that's also an option, and then we can read them out loud.
I think meanwhile I will start to showing some demonstration. I think that because it will take time. So yeah, I talk a lot about the satellites, but how you can use these satellite data sets. So very recently, a new system has came into the picture for analyzing the satellite data sets. So very lately, NASA has realized that not even NASA, but NASA and ESA both has realized that they have a very big server where they put all the data sets from the different satellites for multiple years. And now everyone is downloading those data sets in their local machine or local storage systems. And you have a multiple copies of these satellite data sets, right? And that actually leads to the space crunch. So you have already you have a limited space, and now you are just putting some copied data sets. So now this question actually came into the one of the conference, and now they thought we have to do some development to get rid out of this, because the space is very much important. So NASA, what they have done, they combine all their platform. So they have a multiple satellite launch for atmosphere purpose, maybe for ocean purpose, maybe for cryosphere purpose. They combine all that and they put in the one platform we call NASA Earth Data Search. I think probably a few of you already know about this. It's called Earth Data Search. So in that you can, oh my God, what are these lines? I don't know. So this NASA Earth Data Search has all the data available. You can download the data sets from here if you want, but there are another system they develop. So they try to sift all these data sets from their own server to one of the cloud platform, which are footed in the US West 2 region, which is nearby Oregano region of the USA. And that cloud platform called AWS. So this Amazon is providing this facility to the NASA. So AWS, they are putting all the data into there. Still, the work is in progress. So not all the data set has sifted, but yes, a lot of data sets has sifted there. So now the benefit of this cloud platform is that you can directly access those data sets from the cloud without downloading them. So that will save your time, and that will also save your space. So how we can do that? Maybe I'll just quickly show a couple of things. And the similar work ESA also is doing. But yeah, I just cover the NASA side first, because that is an easy way cover within half an hour. ESA side is a little complicated. So how we can do that? Okay. Ta-da. Okay, so I prepared one Jupyter notebook to show that how we can access the MODIS and the SPEX1 datasets from the base. So there is a library, Python library called Earth Access. So this Earth Access is developed by the NASA and the group. So based on this Earth Access will help you to directly access those datasets, put it into the cloud in AWS. Now for that, we need an authentication. So once you have the account in the Earth Data Search, you will have the authentication to directly use the data from the AWS. Maybe I will quickly log in and show you. Yes, and this also affect this connections between the cloud platform and your local machine also affect by your internet connection. So make sure that you have a proper internet. Otherwise, when you start running the code and in between, you will get a lot of disturbance. So yes, now I am into the NASA data search. You can search any of your product like SPEX1, Miser, Calypso, MODIS, whatever. I search SPEX1. You can put some temporal. I'll just quickly put some numbers. 17th. This is because I know this date. Just yes. Apply. Now your data is filtered for this particular date. I will put some special region also. Okay. Just a small region, so just to see the Indian pollutions for the particular date. And you'll see that you will have a multiple PACE SPEX1 data set, level 1, level 2, level 3. We are going to use level 2. Now there are two versions of level 2. One is the NRT, which called near real-time product. So near real-time products are not accurately retrieved. So you can see, so yes, and one more thing I forgot to mention, that the SPEX1 will provide you data separately for land and for ocean. So you can see PACE SPEX1 level 2 regional aerosol optical properties over land, Ramotep algorithm version 3. And the similar you can find here, it is for over ocean. So when you use the data set, you have to use for both over ocean and land, depends on your region. So for now, I just selected the land portion, so I'll just use the land. And we have another one is near real time and the well-developed products. So in near real time, I can't find right now, but yeah, in near real time, you can find the NRT written here. So this is not NRT because it is well developed. But if you'll see for the given space and the time, we have a one granule available. Granule is like the one orbit, which are divided into the multiple file. So the one section of the one orbit called the granule. Now, once you select your product, now you can see that how many files you have within the given area. So we have a one pass during that time. So as I mentioned, SPEX1 has very narrow swath. So you won't cover like the entire region, but yes, you will have a small portion of the regions as covered by the SPEX1. Now, if you see, this has the, okay, yes, this collection detail. So based on this collection detail, you can understand that what kind of product is PACE SPEX1 level 2 AER aerosol product. RT is the Ramotep algorithm, and land, so land, the version 3. And now these informations we need when you access the data from the cloud. So you can get this information from here. Now I'll switch to the Jupyter notebook. So this Earth access, as I mentioned, it's the library you can use directly to access the data from the cloud. So once you write import Earth access, then we have authentications. Now these authentications, I forget to tell you, that you will get from your account. Go to your account and where is it? Yeah, oh, sorry, no, that is ESA. Sorry, I'm confused. So once you have an account in the NASA datasets, you will have the authentications already by default. Now, whatever your password and the username that you have to save in one of the file netrc and put it on your home directory, or else you can do without the netrc, but at the time you have to enter your username and password here every time. So it is better you just save your username and password in .netrc file and put it in your home directory. So you do not have to every time put your username and password here. Now, once you have this, I think it is visible, right? Okay. Once you have the authentications, so you can see here, I have authentication or data login successful. Now you have to search your product like what we did in the NASA data search. You can do it here same way. So that library called Earth Access has the argument called search data, or the command called search data. Search data has the multiple argument. One is short name. So short name, what I showed you here is PACE SPEX1 L2 AER. So from here you will get the short name that you can write here in short names. So I already wrote here for Modis and the SPEX1. These are the short name for the product. So based on that, the algorithm or the code will identify what kind of product we are looking for. Cloud hosted, it is not required. The older version of Earth Access need that. Right now, we don't need that. Now, after the product selection, we need the special region, which called bounding box. So this bounding box where you have to put your boundary of your region. So I already put it here, search box. This is my lat long of the square region. You can put polygon also, whatever you want to put. You can search on the Earth Access, you will get the information. Once you put the spatial selection, we have the temporal selections. The temporal selection is the date between that two date you need the information or particular time also. So I already choose the 17th of November 2024 and the 17th of November 2024, but between 00 to 23, so all the entire day. So I have a selection of particular region, particular time, particular product. Now what this Earth access will do, so this Earth access will search data option will do, it will go into the cloud platform via Earth access and it will search those data sets and it will filter out for the given space and time. Now, once you have that, if I'll run this code, it will give me that how many files you have within your given time and space. So I have the one Modis file and the one base specs1 file, right? If I want, I can download those files in my local machine. If I don't want to download, I have a good internet speed, I can directly use for processing. So I just commented out the downloading option, but I just showed here if you want to use. So it is very easy, earth access.download and put it your local path. It will download your file. Now, without downloading, we call you directly open the file into the clouds, and that calls streaming the file. Okay, so stream the file. Now for streaming, we just have to use the okay. Yes, earth access.open and your file name. So this open will directly open the file within the cloud platform instead of downloading the file. Now what I did here, I download the, I use the Modis data here. I process the Modis data. So in that Modis data, I extracted the latitude, extract the longitude, extract the quality flex, and extract the very general AOD optical depth, land and ocean, very common variable. And I filter out based on the quality flex. So the quality flex equal to 3 is your aerosol optical depth for the best quality. So that is in the Modis data. So once you did that, you have your data is processed. Similar for the specs1 also. So specs1 has a data stored in a different way. So if I'll quickly show if my HDF is open, let's see. Yeah. So Modis has very easily you can open because that is, sorry, this is the Modis file. Yeah. So those variables are directly, so the Modis file is, first of all, it has a different format called HDF. And in HDF format, these folders, geolocation fields or data fields, there's those folders called groups, and the variables are installed in a particular groups. Now, when you use the Python with HDF library, you do not have to mention the group name. You can directly mention the variable and it will extract. But if you'll see the specs1 data, they are stored in the netcdf file. They also have some groups called diagnostic data, geolocation data, geophysical data. And in that, every group has the different variables. So if you'll see, so geophysical has the ALH, which are aerosol layer height for coarse, fine, mode 1, mode 2, mode 3, which are the different size distribution, what I showed, angstrom exponent, AOD 550, and this AOD, which is available on the 18 wavelength. And then we extracted just 550 and just put it outside for the simplification. And then we have a chorus AOD, fine AOD. We have surface variable BPDF, we have chlorophyll informations, then fine mode fractions, fine mode volume fractions, and then reflective indices MI and MR. They are the reflective indices different for different mode and different for coarse and fine. And we have the effective radius for different mode. Again, we have a spherical fractions, what kind of your particle is sphere or not, that information you will get it from here. We have a single scattering albedo, we have a volume size distribution, effective radius again, and then water fractions, wind speed, and one more processing control. So there you can find some of the factors used for the retrieval. So all these informations are available here, and those informations are saved in a particular group. Now, the issue with the Python netcdf library that every time you have to mention that in which group your variable is available. Based on that only you can extract the particular variable. So if you see that I extracted latitude, longitude, AOD, which are stored in a different group. So these are the group name. And what are the name of the variable within the group, that also you have to mention. So I extracted latitude, longitude, and the quality flag along with the AOD. Now this AOD has the information at 18 wavelengths. Out of that 18, I'm choosing the 550. So it will do by itself. I do not have to mention the index. This is the way how you can extract the particular wavelength informations from the given 18 wavelengths. And then I am applying some quality flags. All these quality flags are used for the identifying the accurate pixels. And once you process these specs1 datasets, you can compare the two different plots. So I have the left side specs1 quality filter datasets, and on the right side MODIS Aqua datasets. Now you can see this is the region where you have the high AOD, which is the pollution area. So I think a couple of days before this date, there was a agriculture burning. So yeah, we don't have the enough coverage. But yeah, you can see some of the signal of from both the MODIS and specs1. The specs1 is high resolution compared to the MODIS, and you have a more information also. So if I'll run this very quickly. So I run this authentication block. I have to, yes. So I got the Earth data login successful. Now I am searching for the dataset. So it's searching for MODIS Aqua datasets level 2 for aerosol optical depth product, and the PACE specs1 level 2 for the land. You can also add multiple parameter, multiple products along with this. So they found for the given spatial region and the temporal region, we found two files, one from MODIS and one for PACE. And yeah, I'm skipping this. Now I will stream the datasets. Now when you open the datasets, it will shows this, like it streamed the dataset. So the file is open. Now this streaming will depends on your internet speed, but normally it is very quick. And also it depends on the file size and how many number of files you are using. That also is the factor which depends. So right now I'm opening the one file. So they are in queue, processing, collecting results, done, the processed file. Similarly, I will do for the specs1. So it is streamed, open, process, done. Now I extracted those data sets from the specs1 and the MODIS, and I'll run the plotting, and it will process the data sets and yes, prepare the plot. So very quickly, you can do all the analysis instead of downloading those data sets. The major thing what you have to understand this library called Earth Access, which are used and the account in the what we call Earth data search. So once you have these two things, you can access this cloud platform easily. Depends on your internet connection. There is one more thing is that Cryo Cloud. So this Cryo Cloud is again this service developed by the NASA, not this one. This is different Cryo. Cryo in the cloud. Yes, so this is the Cryo Cloud. So as I mentioned that this AWS cloud is put in the or is installed at the particular region of the USA, which called US West 2, which is nearby Oregon region of the USA. So if you are close to that cloud platform, your processing speed or the analysis speed will be much higher. But if you are away from those regions, like if you are sitting in the India or Japan or Europe, then the speed is reduced, like processing or analyzing speed. And that also varies based on your internet connection. So there is to deal with that issue, the Cryo Cloud, which is again sponsored by NASA. So they put additional computers or additional, so don't confuse with the name. It's not a cloud. It's kind of a cloud, but not a cloud. So they put additional computer next to the US West 2 region where this AWS cloud has there. Now, once you have access of Cryo Cloud, you can just connect with the Cryo Cloud. Whether you are sitting in the Japan or whether you're sitting in the Europe, you can directly, your machine is directly connected to next to the AWS because the Cryo Cloud is next to the AWS. So once you connected with the Cryo Cloud, you will have the proper speed for streaming or downloading the datasets. Processing will depend again on your local system. but the streaming of data sets will be much faster. Now, this CryoCloud is still a closed community. I already have an access, but if you can ask them directly, and normally they can provide the access if you can provide the valid reason to use the CryoCloud still. But the limitation of CryoCloud is that the free version of CryoCloud access will provide you the limited hardware access. So how many number of RAMs and how many number of CPU you are getting, that is limited in the free version. And even the storage space is also limited. Once you have processed your data sets, you can shift your data set from CryoCloud to your local machine. Or if your project is allowing, you can go for the paid version and get more hardware access from the CryoCloud. But benefit of CryoCloud is just your processing will be fast, and that will also make sure that whether your internet speed is low or not good, once you process the data on the CryoCloud sitting next to the AWS, so that will be handled by them. You don't have to worry on that. So if you can get an access, you can write the community. They are available on Git. You can write them, get an access, use the data sets. Now, this is the actually basic thing what I want to cover, that instead of downloading the data sets and wasting your time, you can directly access those data sets and do the same analysis what you want to do without downloading the data sets. So yeah, that's all for the demonstration. If you have any question about the accessing the data sets, you can write to me. There are the document available for Earth access, as well as how you can use the data sets. And once you order the data sets from the, so here I have the data sets. Okay, I can show you if here quickly. Yes, so I have this one file. If I download all file, I'm not going to download, but I just want to show you one thing. Yeah, so when you start processing, you can see AWS S3. So that is the cloud platform. You can directly use this link to access those datasets if you know how to use with using the HTTP, or you can see there are the script also available for downloading datasets, but I will choose not to download those datasets. So once you have the access of AWS directly, you can use this link either for downloading the data or directly accessing datasets. And this is the region what I was mentioning about US based 2. That is the region where AWS has installed and what all the datasets are moving to the cloud platform. So this is the one what I was mentioning about. So this directly you can access by the Python library in your code instead of struggling with the data search account. So I think this is a shortest way or the fastest way to use the data sets without getting any space crunch. So yeah, for now, I'm done.
So, Dr. Piyush, I had a question.
Yep.
So this is very interesting because yes, there is data crunch. Sometimes we just download the data, we put it in a folder, we forget, we download again. So yes, but from your practical experience, like today we see one granule being loaded and then we're able to plot. It's pretty fast for a demonstration. How much from your own experience are you able to see, like how much of a data you can load, a week, a month, and then it processes, how long it takes usually? Like different places, there's different internet speeds. Obviously, from Nepal, it'll be very difficult to have that speed. But I just want to know how much it usually takes, like from an analysis
That's a very
perspective.
interesting. Yes, it's a very interesting question. So I recently used like a 1 year of data sets of Harp2. But that time I was sitting into the UMBC next to the US. So the thing was very fast, quick. But again, I said streaming a data set depends on your internet speed when you don't use CryoCloud. When you use directly what I showed here. So the streaming only is the issue, but it is not that difference. Like when you use the CryoCloud, the things will be different like in hours or days. No, it won't that much difference. So you can directly use, but yes, you have to make sure that your speed your internet has to be a continuous, I will say. Other than that,
Yeah.
processing will either you can download the data sets or directly use from the cloud platform. The processing depends on your local system hardware, right? How strong you have hardware. So both the way it is same. Only you need the continuous internet access. That's only we need. So I'll say I use 1 year of data sets. That was pretty quick compared to downloading the data sets, and I will waste my time to download the data set, because when I use those 1 year of HARP2 data sets, each file was 700 to 1 GB file, and I use global data sets. Now you realize the one orbit itself or one granule itself is a 700 to 1 GB. The whole globe data, that to 1 year of data sets, it was in TB, more than TB, but yes, I did without any issue, and the work has done within a couple of days. So I think
even multiple granules, you want to do regrading, you want to like plot out climatologies, it's going to be fast.
It's going to be fast, yeah. And you don't have to download the data set. So that's a very quick thing.
Yes, that's the major advantage. Yes.
And the second thing is that if you want to use multiple data sets, what I showed here, like Maurice and the specs one at the same time, you can directly put one additional product and you can do that instead of downloading the couple of files for the different regions and all. So yeah, so that's an advantage. Yeah.
Yes. Thank you.
Yes, I'll be open for the question, maybe if anyone have.
Anyone has any question, and put it on chat box or ask away.
I don't know how these yellow lines came in my screen. Is it visible? Oh my goodness! I just realized.
So I think we don't have any questions. So Simone,
nice.
What do we do next?
Well, if there's no more questions, then I stop the recording, and then that's it for today.
Okay.
Thank you.
So, Dr. Piyush, thank you so much for taking your time out and giving us this informative session. And thank you.
Thank you so much.